Alrighty, we're on section 10.4, page 291 of your student journal. And the section is proofs with perpendicular lines. Essential question: what conjectures can you make about perpendicular lines? And if my vocab isn't rusty, a conjecture is a guess. It's kind of like a hypothesis. Let's see. Define conjecture. An opinion or conclusion formed on the basis of incomplete information. So it's like an educated guess, but off of incomplete information. Okay, let's go through these theorems. If two lines intersect, so two lines meet at a point to form a linear pair. Man, this is definition is extremely vocab heavy. Linear pair of congruent angles. So first of all, linear pair. Line, pair means two. Well, this angle right here and that angle right there combine to make this line. So 1 and 2 are a linear pair to form H of congruent angles. Oops. So the angles have to be, they have to have the same measure, right? So like if one angle is 10 degrees, the other one is 10 degrees. If one is 30 degrees, the other one is 30 degrees, whatever. You know the angles have the same measure. Then the lines are perpendicular. And why is that? Well, think about how much a line is. Oh, sorry. The lines are perpendicular. What does that mean? The lines form a 90-degree angle. So first, linear pair. Okay, well, they form a line. Okay, that part's kind of obvious. Linear pair. Congruent. What does that mean? Congruent, if they have the same measure, you'll see that they have the same number of, I don't even know what to call these, just the same number of marks, right? There's one mark here and there's one mark there. If there were two marks, as in this one look like this, then they would not be the same measure because that would be 1 and that would be 2 and they would be different. But they're the same number of marks, so we know that they're the same or that they're congruent angles. Then the lines lastly are perpendicular. So if you look at this, like, oh, this forms a 90-degree angle. So perpendicular means, oh, they make a 90 degrees. So really, even though this picture doesn't show it, since it forms a line and a line is 180 and these are equal to each other, the only two angles that are have the same measure and add up to 180 are 90-degree angles. So even though it's not in the drawing, we get to make this conclusion that, oh, well, if they're the same and they make a line, then they are perpendicular. So that's a thing you get to add. You can add it to yourself to the drawing, or you could just keep it in your mind where you're like, okay, well, they're equal to each other and it makes a line, so they each must be 90. Yeah, but the only reason you know that they're congruent is because you have these symbols. If you don't have them, or if you only have one of them, then that doesn't really mean anything. Like, they're not congruent angles. Okay, in a plane, if a transversal, so this is the transversal, it's the line that crosses the other two. If a transversal is perpendicular meaning it has this right angle, 90-degree mark, to one of the lines, then it is perpendicular to the other line. So basically what the perpendicular transversal theorem says is, oh, if you have two parallel lines, then the transversal, and you have the transversal is perpendicular to one of the lines, then it must be perpendicular to the other line as well. And the reason for that is because if lines are parallel, corresponding measures are congruent, or corresponding angles are congruent. And so it's like, oh, if this one is 90, well, then this one must be 90 as well. And if this one is 90, using the, what is it called? The linear pair perpendicular theorem, it's like, okay, well, if this is 90 and these make this angle and the left side angle make a line, then this must also be 90. And then you have, oh, well, then if this angle and this angle make a line, then they must also be 90. And all this is the linear pair perpendicular theorem and not the perpendicular transversal theorem. The perpendicular transversal theorem basically says, oh, okay, well, if it's perpendicular to one line, then it's got to be perpendicular to the line that is also parallel to. So, or sorry, if J is perpendicular to H and K is parallel to H, then J must also be perpendicular to K. I misspoke and said something about J being perpendicular and parallel, but you can't be those things at the same time. Okay, lines perpendicular to a transversal theorem. In a plane, if two lines are perpendicular to the same line, then they are parallel to each other. So this was perpendicular transversal theorem. If it's perpendicular, if a transversal is perpendicular to one line, then it is also perpendicular to the parallel line. This is the other way around. Lines perpendicular to a transversal theorem. If I have two lines that are perpendicular to a third line, this transversal right here, then they are parallel to each other. And so I can add on to this drawing. Oh, well. So if they both have a 90-degree symbol, or a perpendicular angle symbol, to the same line, then they have to be parallel to each other because that's the way it works. So this section, all this is showing you is that the fastest way to a line, the fastest or shortest way to a line is straight. And so we have this perpendicular angle right here to show you, oh, this is the fastest way to that line. And it says find the distance from point A to segment BC. So for instance, you would just use the distance formula, which if you totally forgot, I understand. So we have x2 minus x1, distance equals squared plus squared. And since it's been a little while, I'll remind you that it doesn't matter which one. So like from point A to BC, then we should be using this segment right here because it has the perpendicular symbol here and so on and so forth. Wherever you see the perpendicular symbol, you just know, oh, okay, well, this is the shortest way. And so we have x value. So I'll just do number 1 all the way through, but it's pretty much just a reminder because, oops. Okay, well, no, what the heck? Okay, so we have -3, 0, and we have -1, -2. So I'll take the x's and I'll subtract them. So -3 minus -1. Square plus, oops, this is for that parentheses, this one is for that parentheses. -3 and then 0 minus -2 square. So -3 minus negative becomes plus. -3 plus 1 is -2 square plus 0 minus -2 is 0 plus 2, which is 2 squared. And don't forget to square root all this. So -2 times -2 is 4. Positive 2 times positive 2 is also 4. So I have 4 plus 4, which is 8. And let's use the calculator. Square root 8. You can use your scientific calculator, or you can use Google. It's completely up to you. So square root of 8 is 2.828. Let's just round it to the nearest tenth. The 2, so 2.828. Oops. 2.828. And then there's no directions for what we should round to, so we can leave it. Or we could just round it to the nearest tenth. So the 2 means that the 8 doesn't have to change at all, or it rounds down to 8. So say 2.8. And yeah, that's the only example you should need for all these, because we've done distance a bazillion times. So distance, 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 etc., etc. Make sure you round. You can use a calculator, or you can use Google's calculator. Okay. In exercise 5 through 8, determine which lines, if any, must be parallel. Explain your reasoning. So we're going to be referring to the the 2 theorems, or 2 or 3 theorems we learned earlier. So let's see, just so we can compare, or so I don't have to keep going back and forth. So we have 1, 2, 3. So this one is for lines to conclude that lines are parallel. This one is to conclude that lines are perpendicular. G is perpendicular to H. And this one is to conclude that lines are perpendicular, that J is perpendicular to K. So let's see. It says, determine which lines, if any, must be parallel. Explain your reasoning. So if we're looking at that, then we should be using the lines perpendicular transversal theorem, because it's the only one that proves parallel. This one just proves perpendicular. This one proves perpendicular. But this one is for parallel, this symbol right here. If M is perpendicular to P and N is also perpendicular to P, so I have to see 2 right angles. Well, do we see any right angles here? No, we don't see any perpendicular angles at all. So there's no information for us. So we could say, oh, none. Annoying thing with spacing. None. Let's see if I can do this instead. Oops. No. Okay, none. We don't know anything about the intersection of lines Q and S. As in, we don't know anything about this to say to say anything about anything. Okay, so let's go here. This is just a trap. We don't know anything. It tells us literally nothing, so it's useless. So we can't say R is parallel to S or anything like that. But we do know that this angle is perpendicular, or 90 degrees. And then everything else around it must also be perpendicular, because they're all linear pairs. So this and this must be 90 degrees, this and this make 90 degrees, this and this make 90 degrees, and then same here. So since these angles are the same, and they are corresponding, then what lines are parallel? Well, the lines that are related are P and Q. Again, we cannot say anything about R and S because we don't know anything about these, so it's useless. So we can go ahead and say, oops. P and Q are parallel by the lines perpendicular to a transversal. So 2 lines perpendicular to a third line. In this case, the transversals are lines perpendicular to a transversal theorem. And then if you're not like, this is just extra. R is the transversal, if you're not sure. Okay. Next. So let's see here. This we know nothing about. So we will basically ignore this. We don't know anything about it. Ignore it. So what can I say instead? Well, if this is 90, then the linear, by the what's it called? Linear pair perpendicular theorem. Or sorry, no. Oh yeah. If two lines intersect to form a linear pair of congruent angles. So I don't see the congruent. Oh, okay. So sorry, this is not a linear pair perpendicular theorem. It's like the linear pair theorem or something. Yeah, I think it's a linear pair theorem that angles next to each other and form a line must add up to 180. Well, if this is 90 and this is supposed to add up to 180 with it, then it must also be 90. So I can conclude that for all of these. Right here, right here, right here, right here. I can do this too. So all these are perpendicular angles. So yeah, that's all information I can draw. Now let's try and conclude. Well, oh look, these are corresponding angles, and they are congruent. So since J and K are both perpendicular to M, and actually I didn't even need to do that because it's perpendicular here and it's perpendicular here, which totally counts. But I could say, okay, J, oh, don't do that. Use theirs. J and K are parallel because they are both perpendicular to M. And this is the lines perpendicular to a transversal theorem. And then that's that part. And let's see if we could say anything about M and N. Oh, even though this is useless, oh, what about right here? M is perpendicular to K, and N is also perpendicular. Oh my goodness. M is parallel to N because they are both perpendicular to K. So this is the also lines perpendicular to a transversal theorem. So once we establish that M is parallel to N, now we can also say that all these angles are perpendicular angles because if they're parallel, so I had to look at this to establish that they are parallel, but once I did, I can say, okay, well, if they're parallel here, then they still must also be parallel here. Then if this is 90, then because of corresponding angles, then this must also be 90, and then this must be 90, and this must be, and so on and so forth. Okay. Last one. We see that these are congruent to each other. So what does that mean? Well, by the linear pair perpendicular theorem, if two lines intersect to form a linear pair of congruent angles, which they are congruent and they form a line, then they are perpendicular. They're perpendicular to S. Or sorry, line N is perpendicular to line S. So if 90 and 90, and then do that here as well, because they're all linear pairs. Let's see. So I have this and this. Oh, okay. So I can go ahead and say M and N are parallel because, well, I just established it. And then right here as well, S and T are also parallel. So in number 8, M and N are parallel, and S and T are both parallel. So it's actually just like number 7. So that's it for establishing when lines are parallel using the fact, using like linear pair relationships, using perpendicular angles, and so on and so forth. Let me know if you have any questions.